Hello, everyone. Welcome to season 2 of the Knowmads podcast. I'm your co host Prachi.
And I'm your co host, Bhavya.
Since season 2 was long overdue, we had to start with someone who's not just had a remarkable academic journey in physics, but also someone who's been a great mentor to all his students, and really to everyone who walks into his office. So, in this episode, we're sitting in the office of Professor René Bellwied, a leading experimental physicist and a core member of the ALICE collaboration, which stands for a Large Ion Collider Experiment, one of the major experiments at CERN's Large Hadron Collider, or the LHC. A few days ago, along with his colleagues, he received the 2025 Breakthrough Prize in Fundamental Physics, which is one of the most prestigious awards in science. We talk about the early universe, the beauty and chaos of large scale collaborations, and what the future of physics might hold. Whether you're someone who thinks deeply about the universe or someone who just loves hearing how big science gets done, there's something for everyone. So, let's go.
Professor René Bellwied, welcome to the Knowmads podcast. We're excited to have you.
Thank you. Thanks for having me.
So, first of all, congratulations on winning the 2025 Breakthrough Prize in Fundamental Physics. This is big. Could you walk us through some of the key contributions, particularly by the ALICE collaboration, that led to this award?
Sure. So first of all, let me say that the prize this year was given to all 4 LHC experiments, so the experiments that are working at the Large Hadron Collider. If you look at the group of people that is working there right now, you see it's about 11,000 people. And the prize was given out to all the people that were working there between 2014 and 2025. So I think the cutoff was July of 2024, and if you look at that number, it's 13,000 people. So 13,000 people got the breakthrough prize right now. We're fond of it at the University of Houston because the University of Houston is the largest university group in the ALICE experiment, which is one of the 4 experiments at the LHC. But it is also quite unusual to give the prize to so many people at once. So if you're used to any kind of science prizes, so the one is the Nobel Prize, it is limited to 3 people that can get it in any given year. What the breakthrough people have done is they have awarded effectively the field of science that we're working on. They felt that was the breakthrough, what we have achieved over the last 10 years at the Large Hadron Collider. This has happened with the Breakthrough Prize once before. In 2016, 5 neutrino experiments got the Breakthrough Prize. And I'm mentioning that because there was also a group from the University of Houston that got that Breakthrough Prize, our neutrino people down on the 4th floor. So you have to look at it as a communal prize to some extent. The money will be, and it's a high valued prize because it's the biggest science prize in the world. It was initiated by some philanthropists some 15 years ago, I think. And it's the people you know when you think about philanthropists. So Bezos, Zuckerberg, Milner, Brin. So the whole Silicon Valley felt that science should be awarded significant amounts of money for any breakthrough they make. It was also interesting to see that the Breakthrough Prize has only 3 categories: mathematics, fundamental physics, and life sciences. Right. So it's different, for example, from the Nobel Prize, which has, besides science, also literature, peace, and so on. So this is really a science prize, but even within science, it's a limited number of fields that the philanthropists felt were worthy of breakthrough, if you want, And we're very happy that fundamental physics is one of those categories. So we got it this year, and it was awarded as a lump sum of $3 million. And the purpose of it now is to support travel of young scientists to CERN to do their research there when they're coming from abroad. So it's actually quite helpful for us in the U.S. too. We will take advantage of it as well. It's distributed. So if you look at the makeup of the 13,000 people, 10,000 of those 13,000 sit in the two high energy experiments at CERN, at Atlas and CMS. And then about 1,500 of them in ALICE, that's our experiment, and 1,500 of them in LHCb, which is the fourth experiment. Each of these experiments has a slightly different purpose. Atlas and CMS had originally the purpose to discover the Higgs boson, and they discovered the Higgs boson early on in the running. So, ALICE or LHC right now is running for almost 15 years. It started in 2010. I think we made the announcement of the Higgs boson in 2014. I'm not really sure whether that's the right year or not, but about that time, so 4 years after turn on. And since then, Atlas and CMS have moved on to do other physics, in particular physics, searching for physics beyond the standard model. ALICE has a slightly different purpose. LHCb too. Let me talk about LHCb first. LHCb is looking for new states of matter, exotic states of matter, which is an overlap with ALICE too. ALICE is also looking for exotic states of matter, and LHCb has found a good part of them, and we have found another good part of them. So that's, but the main purpose of ALICE is really the characterization of a new state of matter that we believe existed very shortly after the Big Bang. So the energies that you can reach at the LHC bring you back in time to about the energy density that you had about a microsecond after the Big Bang. Right. So this is enormous temperatures, 10 to the 12 Kelvin, about 100,000 times the core of the sun. It's the highest temperature ever generated by mankind through accelerator physics. And when you look at that temperature, we believe that matter at that temperature went through certain phase transitions to come to the matter that we're used to and that we know today, like protons, neutrons, and other elementary particles. At that time, these particles were not fully formed yet, so they were in a state that we call the quark-gluon plasma. And that quark-gluon plasma was postulated as a state in the 70s by a group of theorists. And the whole purpose of LHC and of the relativistic heavy ion collider at Brookhaven, which ran before the LHC, was to discover this state of matter. And it was discovered at RIC, so the discovery was made in 2005. That was the announcement of finding the quark-gluon plasma and finding an interesting feature in it, namely that it behaves like a liquid and not like a plasma, right, which gives us some idea of what's going on with the evolution and the distribution of matter in the universe nowadays. And we can attribute that to some extent to the fluid dynamic behavior of the early stage of matter inside the quark-gluon plasma. So that happened before the LHC turned on. So when the LHC turned on, the purpose of the LHC was then to look at this plasma in more detail and find out, characterize the plasma, find the what we call the state variables that make up the plasma, and then also find the matter that is formed when that plasma transitions back into protons and neutrons, which happens in situ effectively in the experiment in every collision that we have. So we're colliding two heavy ions together. We make a small fireball of plasma, and then we look at that small fireball of plasma over a period of time when it cools, de-excites, and goes through this phase transition. I see. So it lives for a very short amount of time, 10 to the minus 21 to 10 to the minus 22 seconds, and then it goes back through that. So you cannot measure the plasma itself. What you measure is the debris that comes from the excitation and de-excitation of that plasma state that then ultimately hits your detector. And it hits your detector after a few nanoseconds. So you're talking about, 10 orders of magnitude of time that have passed between when the plasma was formed and when you actually get your debris. And that is still very, very fast, a few nanoseconds, but it is much slower than the plasma de-excitation itself. So we have contributed to this through particular measurements. So we have, first of all, at the beginning at the University of Houston, made measurements of the collectivity of this plasma. So we measured the the fact that it behaves like a liquid to a very high degree. So we measured how ideal the liquid is. We measured how well that liquid can be described by effectively the most fluid medium that you can produce. And then we measured that the constituents that carry that liquid behavior are quarks and gluons and not protons and neutrons. So we have proven that it's a quark-gluon phase by measuring something that is called quark scaling. So we can show that the hydrodynamic behavior is carried by quarks and gluons and has not developed after the phase transition by the protons and neutrons that would then be in the phase. So you therefore effectively prove that you have produced a quark-gluon plasma, because the plasma itself then behaves collectively. It flows together in a certain direction. So you make a direction measurement. You say, I'm giving the plasma a certain tilt, and I see whether that tilt leads to a flow component where all the particles that hit your detector flow in a particular angular direction. And that was measured very early on at the University of Houston. And it was my colleague, Dr. Timmons, had the lead on this. He did most of those measurements. My own group, so part of our group that I'm guiding, mostly looked at exotic states of matter. So we looked at the production of antimatter, which is a pretty big deal because people, when they talk about antimatter, think of antiparticles. So antiprotons, antineutrons, everybody is used to that. But what we have shown is that these antiprotons and antineutrons, when produced in good quantity, actually form antimolecules. They form antimatter. They form antihelium, antitriton, antilithium. We didn't get to lithium yet because we don't have enough antiparticles, but we measured a lot of states in the hydrogen and in the helium sector that show that antimatter, when you leave it alone, behaves exactly like matter.
Right.
So you could potentially go on and then fill a whole table of elements with anti-elements if you have enough antiparticles to make those antimolecules. We spent some time on that. Then we investigated the production of multi-quark states. So if you look at the universe today, it's made out of 2 quark or 3 quark states. We measured 4 and 5 quark states, so-called tetraquarks and pentaquarks. We measured them in several experiments at the LHC, and ALICE being one of them. We looked at hypernuclei. That's also an exotic form of matter, which might be very interesting for dense stellar objects like the core of neutron stars and things like that. So we measured there that, first of all, we measured that strange quark production is significantly enhanced when you go to a quark-gluon plasma. So normal nuclear matter would not make a lot of heavy quarks, but a quark-gluon plasma, with the energy that it contains, makes a lot of heavy quarks. So all of the matter that we have right now in the universe is solely made out of up and down quarks. At the Large Hadron Collider, you make a lot of strange charm and bottom quarks. We don't make a lot of top quarks; they're simply too heavy. But you make a lot of strange charm and bottom quarks, and we can show that because a strange quark has the same partial charge than an up quark, you can replace an up quark with a strange quark, and when you do that, you can still make matter. And that means it replaces a neutron in a nucleus that is made out of protons and neutrons with a lambda particle. That lambda particle then makes what's called hypermatter. So you make hypernuclei. These hypernuclei could be one of the states that drives the heavy mass of a neutron star over a relatively small volume that you have in a neutron star. So a neutron star is a star that has about the size of Houston and the mass of the sun. So you have very compact matter that generally is not achievable from everything we know by just taking neutrons and protons. So there must be something else in there. And that would be one of the possible states. So we have shown that that state exists at the beginning of the universe. Whether it really transforms into, whether it still exists in stars that you see right now, we don't know yet, right? We're working on that. We have to have some stuff that we're working on. We've done more things. I can go on. I'm not really sure where you
Right.
want to
Yeah. So, I mean,
start.
yeah, that's right.
Yeah, I mean, you like that was amazing, and you like talked about some of the very interesting stuff, and we will circle back on that. But I want to know something that I'm sure you've heard a lot of times, but we want to take your opinion on it. How did you get interested in physics, and like from that, how did your journey to Ali start? What happened? Like, was there a mentor? Is there something that nudged you in that direction? What were the early days of this whole thing?
Yeah, I have a quite interesting career as soon as I hit the university, because before I was just I was just a geek. You know, the thing that I liked the most that my parents bought me was a chemistry lab. So I got a chemistry lab when I was like 12, and you know, I made a lot of smelly stuff, a lot of colorful stuff, and blew up my room once or something. You know, I was really fascinated by chemistry. And I actually went to the university and I studied chemistry.
Oh, interesting.
So I got a PhD in chemistry,
Oh,
actually.
wow.
I went all the way through. And then when I you know, worked in my PhD, I got very frustrated with chemistry, because I think chemistry is very exciting. You can make things, but chemistry often doesn't answer the question why you made the thing you made. So you can make exciting materials, and I think that also bleeds into physics. You know, my material science, there's a lot of trial and error to find the right material.
Exactly.
And that's okay. I mean, people should do trial and error for all the applications, be it solar cells, be it, you know, new batteries, catalytic converters, whatever. You need to try a lot of different things. The molecules are very complex, but you never really fully understand why the molecules do what they do.
Right.
And because they're too complex to do it, right? And that kind of frustrated me, and that brought me to physics, you know. So then I packed on a second degree. I got a degree in nuclear physics, because the nucleus made the connection to the chemistry. So you have a nuclear chemistry, and then you go from nuclear chemistry to nuclear physics. And I got that second degree at a national lab in Germany. I got it at the GSI. And that was a nuclear physics experiment, using nuclear chemistry to do nuclear physics measurements. So at that time, I started to look at discovering super heavy elements.
Okay.
So when you look at a nuclear chart right now, there are some, the heavier the element gets, the more it decays, the easier it decays. And we tried to find what was called a new island of stability, where you would get super heavy elements that could potentially even be stable in a configuration that is seemingly very unstable when you look at it from the number of protons and neutrons that you have. We didn't find it, you know, but that connected me to some people at the National Laboratory here at Brookhaven. And I found a mentor who came from my original lab in Germany, in Mainz, and she became a professor in Stony Brook.
Oh, wow.
And I contacted her and we talked, and she said, see whether you can get a Humboldt Fellowship, which is one of the things the German foundation, the Humboldt Foundation, allows you to do, where they effectively fund half of your trip to your work in America for the first year of a 2-year postdoc position. So I applied for it, I got it, and then I went to Stony Brook and started working at the Relativistic Heavy Ion Collider. At that time, that Relativistic Heavy Ion Collider was not a collider, it was a fixed target. So you have a beam that hits a fixed target rather than you have two beams circulating and colliding. So it only reached a certain maximum energy that you can impose on your fireball, and at that energy we didn't see a quark-gluon plasma. So then we were like, okay, we got to go higher, you know, and then one thing leads to another. And then you go to the Relativistic Heavy Ion Collider, and you go to the Large Hadron Collider. At this point, the path was pretty clear, right? So the path to the discovery, at least, was quite clear. And then the path beyond the discovery was mostly aided by the fact that by having a Large Hadron Collider that was looking for the Higgs particle, you could effectively parasitically also characterize the quark-gluon plasma. So it was also relatively clear to do this now at the Large Hadron Collider in Europe. The path forward from here is much less clear, right? I think we have reached the maximum of what we at this point can achieve with accelerators. There are some ideas to build an even bigger accelerator, but the physics of that bigger accelerator is not very clearly defined yet, I would say. There's a certain, if we would find now physics beyond the standard model, and I think by getting the breakthrough prize at this point in time, after effectively 15 years of running at ALICE, it's also a signature by the people that give you the breakthrough prize that they will encourage you to continue looking, right? But not necessarily give you the funding to build yet the next machine. Find something and then you get the next machine effectively.
But that's true. Historically, such prizes have led to an increase, the amount of researchers in a particular field, which is something I think what you're referring to.
Yeah. I mean, it helps. These groups are big, right? And I think you have to see that all of this science anywhere in the world, not only America, is almost 100% federally funded. There's no foundation money. There is nothing from the commercial sector, right? There are some pieces of overlap, and you have to recognize them, and you also have to cherish them, right? I mean, for example, when the Breakthrough Prize was given out, our Director General was there at the ceremony, Fabiola Gianotti, and Jeff Bezos thanked her explicitly during the ceremony for inventing the World Wide Web, right? So the World Wide Web is an invention that comes from CERN, that scientists use to communicate with each other across, many different countries at a time where there was no commercial application for it. But then, based on the science of the World Wide Web, then companies like Microsoft, Apple, Google, and the people that gave the Breakthrough Prize effectively gave the Breakthrough Prize because we broke through and gave them the World Wide Web at a return.
A way to thank everyone for.
So you have to look, and I think as a foresight of these people, and also the foresight of the federal government, to say that this very fundamental physics leads to breakthroughs that are not the direct path of why you built the machine you built or the experiment you built, but they come in naturally. And there are many of those in terms of detector development, in terms of how you use these detectors in the medical sector, in space and so on. And then, the World Wide Web, it can it's not skimpy, it's not bad. And it wasn't Al Gore who did it.
So a major moment in this history of LHC was the discovery of the Higgs particle. And I remember very vividly growing up, this is back in 2012 or 14, that it made the headlines. The God particle is what made the headlines. And LHC ended up becoming a household name after that. So, and I think this was part of the Atlas and the CMS collaboration. Alice, as you briefly mentioned, so we're going to sort of circle back to that, looks at the properties of quark-gluon plasma. Could you talk to us a little bit about, or what's the argument that proves that the discovery of Higgs is or studying quark-gluon plasma is as fundamental as the discovery of Higgs, and we should continue down that path? And perhaps you could also talk about how this particular ALICE collaboration is different from these other experiments that led to this other discovery back in 2012.
Well, the Higgs is an interesting thing if you look at it with respect to the actual physics, right? The Higgs field gives mass to the quark, but the quark doesn't give mass to the proton. And that is the part that is the fundamental part of ALICE also. So, and it might be also the fundamental part of the next accelerator in America, which will be an electron-ion collider. The reason is that you have 6 different quarks. They span in mass. We measure mass in terms of energy from 5 mega electron volts to 175 giga electron volts. So they span over almost 6 orders of magnitude in different mass. The Higgs gives the mass in principle. In order to give mass to 6 different particles over 6 orders of magnitude, what the Higgs does is it effectively defines a coupling constant between the field and the actual particle that is different by 6 different orders of magnitude in that range. That is not a very elegant theory, I would say. You know, at this point, the high energy physicists are continuing to work on why is each particle coupling differently to the Higgs field. It has to, in other words, it wouldn't do the math. And I think there are lots of open questions that will be answered by ATLAS and CMS. But then when you give this mass to the quarks, you're ending up for protons and neutrons with up and down quarks. These up and down quarks have now a mass of 5 or 15 MeV, 5 or 10 MeV, we don't know exactly, but in the range of 5 to 10 mega electron volts for these 2 quarks. When we generally describe a proton, we say it's made out of 3 quarks, out of 3 what we call valence quarks, that each have a mass between 5 and 10 mega electron volts. The proton has a mass of 1 giga electron volt. So again, you have a huge problem that the 3 quarks that you say are the main constituents make up about 1 to 10% of the whole mass of the particle. So no, they're not everything. They're not. We don't understand the mass of the proton.
Right.
We don't understand another feature of the proton, which is called the spin of the proton. We don't know what carries that. What we know from calculating it on lattice QCD is that effectively there are other particles in the proton that we have to take seriously. There is what's called a gluon field that keeps the interaction between the quarks going. The gluons are massless, so they should not contribute to the mass. But then the field that the gluons contribute can contribute to the mass of the proton, but we don't really understand how. And then there are quark-anti-quark pairs that exist as a form of energy that we call a C-quark that also is a form of energy, not a form of rest mass, that also seems to contribute to the rest mass of the proton. This mishmash of particles that we actually know and forms of energy that we can measure but not really know how they contribute to the proton should be solved by looking at the quark-gluon plasma and how the quark-gluon plasma then de-excites into states that have a mass of 1 GeV rather than a mass of 15 MeV or so. So that happens during the transition of the QGP to particles. And we want to study that. And this has to be studied in detail. So you want to study what the gluons doing differently than the quarks, what the C-quarks are doing differently than the quarks. And going forward, you have the LHC that can probe that heavy ion or the proton now with beams of either protons or ions of different sizes. So we're now going down and we compare proton-proton collisions to lead-lead collisions. So this is our range. Next year we're going to write an oxygen on oxygen to get a system that is small but still bigger than a proton, right? And at the same time, we are proposing an electron-ion collider at Brookhaven. So we decommissioned the relativistic heavy ion collider this year, and then we put an electron beam in, and then we can take the electrons and let them collide with a heavy ion. The difference would then be that a proton is a finite-sized object. It has an internal structure like we just described of protons, gluons, and quarks, gluons, and C-quarks. An electron is point-like, carries the energy in one constituent that, as far as we know, has no substructure.
Right.
So you have a very good control over the energy because it's carried by one point-like particle, whereas the energy of a proton has to be at least distributed over these 3 valence quarks and maybe distributed over more inside the structure of that proton. And those are things where you can now start to compare what you measure with an electron to what you compare by shooting a proton onto your heavy ion to what you get when shooting a heavy ion onto your heavy ion. So you characterize certain features of this phase transition by changing the incoming probe effectively.
Interesting.
I see. So the main goal of ALICE was to study the quark-gluon plasma, which is believed to exist in the early universe. Now that is the big picture idea. But what is ALICE currently doing? Like, what are the investigations that you're particularly excited about?
Well, what we're excited about is that we're gonna, when you think about cutting edge research, at some point it's got to go into a textbook. At some point it's need to be taught. So now we have the quark-gluon plasma, right? It's not enough to go into a textbook. If you have a quark-gluon plasma, you have discovered a state, but you can't describe the state. So what we're doing right now a lot is describing the state. So now we come to how is a state a state? What makes a state? And the states that we're used to are the phases that matter goes through that we know. So the easiest example is always water. Water exists in 3 phases: ice, water liquid, and steam, right? So you can have a gas, a liquid, or a solid. Those are the states that we're used to. Now on top of that, we also have plasma, which is even hotter and even denser than a liquid. So you have 4 states of matter effectively. And now we say the nuclear matter is in the hottest, densest state is a plasma, but a plasma that behaves like a liquid. So that makes it already kind of freaky. It's interesting. So what makes a state a state? What makes a state is that you can describe it thermodynamically. You can describe it in the form of pressure, volume, temperature. That's what we call an equation of state.
Right.
The easiest equation of state that every physicist learns in school is the ideal gas law, right? P times V is nRT, right? That's one of the famous formulas of science. And it says that the pressure times the volume is proportional to the temperature. If you have a system that behaves like that can be described thermodynamically, then that system has certain state variables. So a state variable, for example, is the compressibility. Another state variable is the viscosity. Another state variable is the speed of sound, right? And we spend a lot of time on viscosity by now because that showed us how perfect the liquid is. What we're very excited right now is the speed of sound. So we're now starting to measure the speed of sound in a quark-gluon plasma compared to the speed of sound in a hadron gas, compared to the speed of sound anywhere, right? So what you learn in school about speed of sound is that it's different from phase to phase. Sound travels faster in water than in air. And then when it is in a particular phase, it depends on temperature. So both of these things you can now study with your quark-gluon plasma. You can either see how it behaves in the phase, whether it's temperature dependent in the phase, or whether it changes drastically when you go from one phase to another phase. So when your quark-gluon plasma comes out of the plasma, it goes into a gas of protons and neutrons. So you want to measure it in the gas of protons and neutrons and compare it to what it is in the quark-gluon plasma. In that sense, you could define variables that are unique to the plasma. Unique viscosity, unique diffusion, unique compressibility. And by finding these and measuring these with great accuracy, then you find things that go into a textbook. This is the phase, this phase has these features, and these features are in the textbook, right? That's one of the things. The other one is clearly the question of exotic matter that is not here now, that was there then because you can make it, and seeing whether that changes the way you see the world, right? So tetraquarks and pentaquarks, if they are being found and if they're being found consistently. So one of the big puzzles right now, in particular coming out of the ALICE experiment, is that we have found 4 and 5 quark states that include a charm quark, but we haven't found 4 or 5 quark states that include a strange quark. That's very puzzling. That doesn't make a lot of sense. There's a lot of theory going on about it, but we haven't found that yet, right? This is stuff that we would like to do at the LHC. We have gone with RIC to lower energies because when you look at a phase diagram, one thing the water phase diagram has that our phase diagram doesn't have is a critical point. So a lot of people said there should be a critical point because with the density that you measure, in particular when you go into neutron stars and so on, the phase transition has to change its order from a crossover phase transition to a first order phase transition, and we haven't seen that yet. We haven't seen a critical point. So we spent a lot of time in the last few years on finding a critical point. The theory is more successful than the experiment. The theory seems to hone in on a particular location of the critical point. The experimental evidence is still missing. But we wouldn't look for that at the LHC. The LHC experiments are too high in energy to find that. We're trying to find it at RIC, but there is also a new facility in Germany that might try to locate it there. There is a dedicated facility for that energy regime that you would need in order to find a critical point.
So looking ahead, especially for particle physics or collider physics, with new and bigger colliders being proposed, promising higher energies and so on, what excites you the most? And, what are the big questions that the next experiments will sort of answer?
And maybe also, like, if I play the devil's advocate here, do we even need new and big colliders? I mean, you mentioned yourself, and there's a so-called crisis in particle physics where a lot of money is being, used, and like you said, is this a limitation of where the collider physics can go?
Well, there are two strategies, right? The strategy is go smaller but better, or go bigger, and they come with different physics attached to them. And I think the idea that we always had until now is to go higher and bigger. And my personal opinion, very personal opinion right now, is that this runs against a certain limitation. It runs against the limitation also of any government in the world to saying that this is a high priority to spend taxpayers' money. One should be conscious about this. And if you're conscious about this, then at this point in time, you would say, I can only support this if there would be another discovery at the LHC. The discovery of the Higgs by itself is not enough. I mean, often you hear the arguments that next machine, because, like I said, RIC was a discovery machine for the quark-gluon plasma. The LHC is a characterization machine for the quark-gluon plasma. You could now make that same argument. Higgs was discovered at the LHC. You need what's called an FCC, a future circular collider, to characterize the Higgs. But there is not enough physics in the characterization of the Higgs from my point of view. And here you have to recognize I'm a nuclear physicist. I'm not a high-energy physicist. To say we should go there. I really would like to see physics beyond the standard model. But one also has to recognize that most of the time, besides the Higgs, and I say that Higgs was about 10 years ago, since then we have tried to find physics beyond the standard model, and we have spent an enormous amount of papers on that, right? And we have written 3,500 papers on this, so it's not for lack of trying, right? And we were very, very, in particular CMS and Atlas were very, very, dedicated, precise, and they tried everything you can try, and they haven't found it. Let's be clear about it. There's nothing, right? And so within the realm of the energies that the LHC can produce. But the LHC can produce an enormous amount of energies, from the smallest supersymmetric particle to the largest supersymmetric particle. There is no supersymmetric particle. So this is something that limits the call for the next accelerator. And I think rightfully so, because you also have to see, what are we talking about? 10, $15 billion. And nowadays, it depends on where your priorities are as a government. It depends on where you want to go. But like I said, the next machine in Germany is lower energy, more precision around the critical point. The next machine in America is an electron-ion collider, more precision to find the transition from quark-gluon into proton-neutron. Measurement of the spin, measurement of the mass, measurement of the C-quark contributions, measurement of gluon saturation. There are lots of physics topics that are connected to this transition and this inner structure of the proton and the neutron, therefore, that will be addressed by machines that don't have the same scale than a future circular collider. And so you have to really distinguish. I think accelerator physics definitely has a future, and it has a future, but not a future beyond the standard model. So you work within the standard model. One also has to see that the standard model was very successful, and string theory maybe was not, right? I mean, you haven't found this thing that was postulated, and at this point maybe experiment should drive it rather than theory should drive it, because theory drove it and we didn't find it. So if you have the privilege of finding it, it's also very difficult to build. I'm happy that people are working on it, and one should make proposals, but finding the resources to build those proposals into reality might be difficult without another breakthrough. Right.
That's like the perfect segue for the next question. Like, so you were talking about the future of physics. Where do you think is the next, let's say, the breakthrough? Like, is it quantum gravity, cosmology, something entirely different?
Well, the interesting thing that I'm excited about, and I'm an experimentalist, so I don't necessarily like to dream, right? I like to work with reality. That's the difference between theory and experiment. And when I look in reality, I got to see what's achievable, right? I am very excited about the connection between the physics that we're doing and astrophysics. I'm very excited about the link between gravitational waves and heavy ion physics. I think that's really cool. And it also shows you what a relatively benign measurement, like a frequency spectrum of two stars collide. It's not benign in what happens, but it's benign of what we actually can measure from it, which is effectively one frequency spectrum. How that frequency spectrum, by reaching a high accuracy in the frequency spectrum, can tell us about what the matter is inside the star, what the matter potentially is inside of black holes, if there's still matter left. And we're making this link between two very different fields. The most macroscopic field of physics, which is measuring things on the parsec level or so, and the most microscopic physics. And what we're trying to achieve is, again, what we're very fond of in physics is universality of scale.
Exactly.
You measure something very microscopic and you can predict what happens in the most macroscopic objects that you find. If we can achieve that universality of scale through, making a collision in a laboratory and say that's exactly the same what happens when two neutron stars merge, I think that's an amazing achievement.
Absolutely.
And I think that's an achievement that I'm personally involved and interested in. And, because the next breakthrough to physics beyond the standard model, I will be very excited when it happens, But you have to recognize, I was in Michigan when my university was one of the main proponents to propose LIGO. And that's the measurement that did gravitational waves. we laughed at those people. We were like, what are you guys trying to do? This is like so science fiction. You will never measure a gravitational wave, right? And I didn't get involved because I thought it was too high risk for my career, right? Well, now I might have a Nobel Prize if I would have gotten involved, right? So you cannot predict the future. And I believe that mankind will probably find physics beyond the standard model. But my life is not that long anymore. For the rest of my life, I want to work on something that I can see right in front of me. And that is really that link between high energy physics and astrophysics. That's what I would like to work on. Also understanding the quark-gluon plasma even better than we understand it now, understanding the formation of matter, because I think what we found are very exotic states of matter, not supersymmetric particle, but like I say, hypernuclei, pentaquarks, tetraquarks, antimatter. All of this stuff is new to us, and we really have to see where this guides us, because that could, for example, this big question of why do we live in a matter universe and not an antimatter universe. Now for the first time we have antimatter, so let's study it. Let's see what it does. Let's see where it goes. Let's see how it annihilates, how easy it annihilates, and so on and so on. I think there are still a lot of questions, baryogenesis, leptogenesis, leptoquarks. There are lots of buzzwords that I could give you that is interesting physics that will not be addressed by a future circular collider, but can still be addressed by data that we have already, So there's a lot of stuff there.
So thank you already for your time, but to sort of move to the end, and circling all the way back to the Breakthrough Prize, again, one thing that really stood out, and you touched on this, that this prize was awarded to thousands of researchers spanning several countries and many continents and so on. So you've been part of the scientific community, especially the physics community. You've seen it evolve. What does this say about the future of physics? That are big collaborations the big thing, or how does it contradict the lone genius geek sitting in the corner of a room and doing physics?
Well, that's a good question, because I think ultimately that is also this redirecting resources, right? This is a very collaborative effort of 5,000 people from 70 or 75 nations. So everybody is involved in it, all the way from countries that have a much smaller science budget than America has, in particular like Asia. When you see it, when China is coming up really big, but India also has a big contribution to it. The big countries have big contributions no matter what their, what their resources are really. They could put the resources into other things, but they choose science because they think that this is driving mankind forward, and it absolutely does. And I like science on a big scale, and I like it on a small scale. On a small scale, the big scale, having these collaborations is an amazing experience for young people. You learn, cultural differences, all working on the same science, give you cultural viewpoints on the same science that really drive things sometimes in a direction that you would not achieve by having one nation working on one experiment or something like that. There's a lot to be said about collaborations and how they function, and what you learn from being a member of a functional collaboration, which also brings people closer together, has societal payoffs that we don't even talk about. We talk about the science, but having to deal with people that speak 50 different languages, and they all have to find a common language to talk to each other, and that common language is science and how they interact with each other. There is so much to be said about doing this, about tolerance, about respect, about all of these things that you learn that make it very nice to have big collaborations. Will they at some point become unaffordable? That is a thing that everybody needs to ask themselves, and you have to have good government to ask that question and answer that question properly.
That's right.
And that could sometimes go awry, that could also change back, and then it doesn't go awry. So one has to see how things develop, and they develop differently in different parts of the world, and that you have to work together, that leads sometimes to politics influencing science.
Right.
We parted ways with the Russians after invasion of Ukraine. That is very unfortunate because the Russian scientists are very good scientists. But you have to make political decisions in a framework of science that sometimes are unavoidable, right? And it hopefully it all will work itself out. But yes, a big collaboration runs like a country. It's a microcosm of a country. And that's very different from having 5 people in a lab and working on something. So sometimes you would think, it's so much easier to work with 5 people.
Right.
And it is. You can get probably more done. But on the other hand, you also probably can't work on the big problems anymore when you work with 5 people. Although there are plenty of ideas. But nuclear physics went this way. I think it did very well for itself over the last 30 years. It probably becomes a little smaller again right now. But even if you look at a nuclear physics collaboration at the EIC, which is planned for the next decade, so instead of 1,500 people, you have 1,000 people or 800. It's still not small, right? So, and in the end, it might be also 1,500 people, right? So that might happen. But certainly there is science to be done at the 5 to 10 people level that will also give you something. Science is so broad that you need it all. You need all of that to do what you need to do.
So finally, what would your advice be to the young generation, like the next generation of physicists who've just started to explore the universe?
Well, what I can see is that the people that come through our group, they are very well prepared for whatever comes because they have to deal with these things. They have to give presentations every week. They have to, deal with Zoom, deal with Teams. They need to talk to people on the other side of the continent. They have to get up at 4 o'clock in the morning to give a talk or so. But it prepares them for everything, right? It's well prepared. Now, whether that leads to success is a different question, right? Because it's also very competitive, right? Those 13,000 people, from my point of view, are 13,000 of the best physicists in the world. That's why they got honored for that. But that means you compete with 13,000. Alice last year gave out 260 PhD theses all over the world. But that's your competition, right? But you're working on the most cutting edge stuff. So the question now is, what do you do with it? Not everybody gets a job in the field, but everybody gets a job, guaranteed. So that's number one, right? Number two is how flexible are you? And that comes down to how flexible are you with where you do your work? How flexible are you with what kind of work you do? You get a high-paying job. That's also guaranteed. But you might get a high-paying job because you're really good on your computer. You're really good with machine learning, AI. Those are the things we're using regularly right now. You get some experience with those. Lots of people end up in banks. Lots of people end up in insurance companies, risk management. Lots of people do risk management for the government. Lots of people do jobs that you wouldn't necessarily think about right away. But if you have that flexibility, you get these jobs and you make a lot of money with these jobs, probably more money than staying in science. Right? So
sure. That's
a thing where you might want to early on think about how you want your career to go, right? And if you want your career to be in science and you don't want it to be in insurance or in banking or in Wall Street or any of that, then you might have to work even harder than you work in order to go into these areas, because you from the first day on, you know your competition. That's because they're all around you and you see how they develop, and you see what they do, and you see how they get hired. And from our groups, you're also the theory group, a lot of people get hired in academics, and we're proud of that. But if you see, we also have a lot of people in the group. So again, not everybody gets hired in academics. So but if you want to take that risk, if you want to have the competition, if you grow with competition rather than fail, if you can anticipate that, then this is the most interesting science to work on. There's no question, right? That's obviously true. But, you can say, I feel more comfortable in a small group, and you go into a small group. What I'm always saying to people that come into my office and say, I want to work with you, I always tell them, think very, very hard about this before you make that decision. We're a very successful group. People walk in. But people walk in because we're a successful group. That doesn't mean that you're successful in this group, right? You need to, your advisor is your second father, unfortunately, or mother. It doesn't mean. So you spend at least 5-6 years with me. Those are the most shaping 5-6 years of your career. You got to get along with each other, number one. Number two, you got to really like what you do. And you might choose a thesis topic on a whim. If it's not the right one, and you find out after 6 months or 9 months that it's not the right one, go and talk to your advisor, right? Might not have anything to do with your advisor, might have to do with the topic. But if it doesn't work out, stop as soon as you can and go somewhere else, right? Because if you do that after 3 or 4 years, it's almost too late, and then you go through with it. And then you're stuck with it. Because in the field, people will hire you because of what you've done, right? And you can diversify it, and you should diversify it. So we diversify it by saying you're doing an analysis, but you're also working on a piece of detector. So you learn electronics, you learn different detectors, you learn what you can do with a silicon detector. Like I said, we built a silicon detector for our experiment. It's right now in every mammography device that MD Anderson is using. We built silicon detectors. They're on the space station for radiation damage measurement. So you can take technology and transfer it over into other fields. That's one way you can diversify your career, right? ML, AI, you can diversify your career that way. You learn, you're very proficient with certain computing languages, And clearly it's not C++ anymore, it's all Python now. So you got to go with the flow, right? So in my days, I was really good in Fortran, right? That's the only language that I speak, really. So that's already 20 years old, so you don't do it anymore. So, you diversify your portfolio, you write a portfolio, and then you see what you can achieve with that portfolio when you go into jobs. If you want to go on in academia, make that decision early and think about it.
Yeah.
Make yourself known. Go to as many conferences as you can. Convince your advisor to give you the money to go to as many conferences as you can. And show yourself, right? Give talks, as much as you can. And the more people know you, the earlier they know you, the more opportunities you have. And that's relatively easy in our field because hundreds of people are on every Zoom call where we give a talk or so, And these people will say, oh, I know her, I've seen her, and then I want to work with her. That's the next step, effectively, And then the thesis itself and the proficiency you achieve in certain areas. And when you want to be a postdoc, declare that as early as possible, right? Don't say, oh, I'll think about it when my thesis is done. That's a big mistake,
That is a mistake.
Because we cannot generate jobs in a whim or so, And for industry, you can only apply after. But that decision of whether I go for industry or whether I go for academics, you should make earlier than at the end of your thesis. So try at least,
That was great. Thank you
That
for
was great.
doing
Well
Thank
done?
you.
Okay, good.
Thank you.
Thank you. Thank you for having me on your podcast.
Our pleasure.